A binary search tree, BST, stores keys so that for every node n, all keys in n's left subtree are smaller than n dot key, and all keys in n's right subtree are larger. When we delete a key, we encounter three structural situations. Leaf node, a node with no children, both left and right pointers are null. Think of it as a leaf on a real tree, a tiny twig that can be cut off without affecting the rest of the branches. Node with one child, the node has exactly one non-null child, either left or right. This is like a branch that only has a side twig on one side. When we remove the main branch, we can simply tie the side twig directly to the parent. Node with two children, the node has both left and right subtrees. This is the most involved case, comparable to removing a trunk that splits into two big limbs. We must pick a replacement that preserves the ordering. The usual replacements are the in-order predecessor, the largest node in the left subtree, or the in-order successor, the smallest node in the right subtree. Step by step for deleting a leaf node. Search for the key using the BST property. Go left if the key is smaller, right if larger. This takes big O of h time, where h is the tree height. Confirm that the located node is indeed a leaf. Node.left equals null and node.right equals null. Update the parent. If the leaf is the left child of its parent, set parent.left to null. If it is the right child, set parent.right to null. If the leaf is also the root, the tree has a single node, set the root pointer to null, leaving the tree empty. Imagine a bookshelf where each book has a left and right neighbor. Removing a book that has no neighbors, a leaf, just leaves an empty slot. You simply erase the reference to that slot. Delete 5 from the BST formed by inserting 8, 3, 10, 1, 6, 14, 4, 7, 13. Node 5 is a leaf, no children. After the deletion, its parent node 6 will have left set to null. This operation does not require any restructuring, only a single pointer change. Explanation: deleting a node with exactly one child. Let the node to delete be x and its only child be c. The steps are: search for x as usual. Identify which side child is present left or right. Reconnect: set x's parent pointer to c, bypassing x if x was the left child of its parent p, assign p.left equals c. If x was the right child, assign p.right equals c. If x is the root, i.e., the tree's only node has one child, make c the new root. Real-world analogy: think of a train car x that is connected to the rest of the train only by a single coupling C to remove the car. You simply connect the coupling directly to the car before x, eliminating x from the chain. Example: in the same tree, delete node 14, which has only left child 13. After deletion, node 13 becomes the right child of 10, preserving the BST ordering. Only one pointer needs to be updated, so the cost is still O of h for the search plus O of 1 for the reconnection. Deletion using the in-order predecessor, largest node in the left subtree. When the target node x has two children, we replace x's key with its predecessor's key and then delete the predecessor, which is guaranteed to have at most one child. It cannot have a right child. Steps: locate x by searching for the key. Find predecessor. Go to x.left, then repeatedly follow the right child until reaching a node p where p.right equals null. Mathematically, p equals the maximum of y such that y is in the left subtree of x. Swap values, assign x.key equals p.key, the structural links stay the same. Delete p, because p has no right child, it falls into case 1 leaf or case 2 single left child. Apply the appropriate leaf or single child deletion steps to remove p. Analogy: imagine a ranked list where you want to remove a middle entry but keep the ranking intact. You copy the rank of the person just above, predecessor, into the slot, then remove the original above person entry, which is now a duplicate. Example: delete 8 from the original tree. The predecessor is 7, the maximum in the left subtree rooted at 3. Replace 8's key with 7, then delete the original node 7, which is a leaf. The final tree remains a valid BST. The key insight is that the predecessor is the rightmost node of the left subtree, guaranteeing that after the swap, all left subtree nodes stay less than or equal to new key, and all right subtree nodes stay greater than new key. Deletion using the in-order successor, smallest node in the right subtree. This is symmetric to the predecessor method. Steps: Step 1, search for x, the node to delete. Step 2, find the successor. Go to x.right, then repeatedly follow the left child until a node s with s.left equals null is reached. Formally, s equals the minimum of y such that y is in the right subtree of x. Step 3. Swap values, x.key equals s.key. Step 4. Delete s. Since s has no left child, it is either a leaf or has only a right child, so we apply the leaf or single child deletion algorithm. Analogy: think of a queue where you want to remove a person in the middle. You let the next person in line, the successor, take the removed person's spot, then the original next person steps out. A simple handoff that keeps order. Example: delete 3 from the tree. The successor is 4, the smallest node in the right subtree of 3. Replace 3 with 4, then delete the original 4 node, which is a leaf. The binary search tree property holds because all nodes left of 4 are less than 4 and all nodes right of 4 are greater than 4. Both predecessor and successor methods run in big O of h time, because the extra walk to find the replacement is bounded by the height of the tree. Deleting the root. If the root has no child, the tree becomes empty, root equals null. If it has one child, that child becomes the new root, simply move the root pointer. If it has 2 children, apply predecessor or successor replacement as usual. After swapping, the root's key changes but the root node itself stays, preserving the external reference. Deleting a non-existent key, perform the normal search. If a null pointer is reached, that is, the key is not found, abort the deletion and optionally return a not found flag. No structural change occurs, so the BST remains untouched. Rebalancing considerations. Simple BST deletion does not guarantee the tree stays balanced. After many deletions, the height h may become big O of n in the worst-case degenerate list. To keep operations fast, self-balancing trees, a VL red-black splay perform extra rotations after deletion. The basic deletion steps stay the same. The extra step is a rebalancing routine that restores the balancing invariant while preserving the BST ordering. Real-world parallel. Removing a manager root from a company may promote a deputy, single child, or restructure the hierarchy 2 children case. If the employee does not exist, HR simply reports an error without changing the org chart. These edge cases are handled by guarding the algorithm with condition checks before performing pointer updates or rebalancing. Explanation: proof that BST property is preserved after each deletion case. We prove by case analysis that after applying the deletion algorithm, the resulting tree T' still satisfies : for every node V. All keys in V.left are less than V.key, less than all keys in V.right. Lemma 1, leaf deletion: removing a leaf node L does not affect any other nodes left/right subtrees because L has no children. Hence, the ordering of all remaining nodes is unchanged, so the property holds. Lemma 2, single child deletion: let X be the deleted node with sole child C. X's parent P originally satisfied either P.key greater than X.key if X was left child or P.key less than X.key if X was right child. Because C is the only subtree of X, all keys in C are either greater than X.key if X was right child or less than X.key if X was left child. When we replace X with C, we set P's pointer directly to see the inequality P.key relation C.key remains the same as P.key relation X.key because C.key is either the minimum if left child or maximum if right child of X's subtree, preserving order. No other relationships change, so the BST property is maintained. Lemma 3, 2-child deletion, predecessor: let P be the predecessor of X, maximum node in X.left. By definition, P.key is less than or equal to every key in X.left, and P.right equals null. Also, every key in X.right is greater than X.key greater than or equal to P.key. When we copy P.key into X, the left subtree of X still contains keys less than or equal to P.key, and the right subtree still contains keys greater than P.key. Deleting P afterwards falls into Lemma 1 or Lemma 2 because P has at most a left child. Therefore, the overall structure after both steps satisfies the BST ordering. Lemma 4, 2-child deletion, successor: symmetric to Lemma 3, using S equals minimum of X.right. S.key is greater than or equal to every key in X.right and S.left equals null. After copying S.key into X, left subtree keys are less than S.key and right subtree keys are greater than or equal to S.key. Removing S, which is a leaf or single child, does not break the ordering. Theorem: by induction on the number of deletions. The BST property holds after any sequence of deletions performed using the described algorithms. Thus, each case preserves the invariant. Time complexity analysis. Let h be the height of the tree, h less than or equal to n, where n is the number of nodes. The dominant work in deletion is the initial search for the key, and in the two-child case, a second walk to find predecessor or successor. Best case, the key is at the root and the root is a leaf. Search takes big O of 1 and deletion big O of 1, so best case theta of 1. Average case randomly built BST. The expected height is theta of log n. Search is big O of log n. Finding predecessor or successor adds another big O of log n in the worst branch. Still big O of log n, hence average case theta of log n. Worst case, the tree is completely unbalanced, a chain. Height h equals n. Search may traverse all n nodes, and finding predecessor or successor may traverse another big O of n nodes, yielding theta of n. Overall deletion time equals theta of h. In balanced self-balancing trees, a VL red-black h equals big O of log n, guaranteeing theta of log n worst case. Space complexity is big O of 1 extra, ignoring recursion stack if implemented recursively. Then stack depth equals big O of h. Given the binary search tree built by inserting the keys 50, 30, 70, 20, 40, 60, 80 in that order, delete the node 30 using the in-order predecessor method. Show the tree after deletion. Tree before deletion, a root node 50 with left child 30 and right child 70. 30 has left child 20 and right child 40. 70 has left child 60 and right child 80. Node 30 has two children. Its in-order predecessor is the maximum in its left subtree, node 20. Replace 30's key with 20, the node now holds 20. Delete the original node 20, which is a leaf. Remove the left pointer of the former 30. Resulting tree, root 50 with left child 20 and right child 70. 20 has right child 40. 70 has left child 60 and right child 80. In a binary search tree, the node to delete has exactly one right child. Describe the pointer changes required when the node is not the root. Let x be the node, see its right child and p x's parent. If x is the left child of p, set p left equal to c. If x is the right child of p, set p right equal to c. Finally, optionally free x. The binary search tree property remains because every key in C is greater than all keys in X's left subtree, which is null, and less than all keys in X's right subtree, which is C itself. No other pointers change. Consider a binary search tree that is already a linked list leaning to the right, with keys 1, 2, 3, up to n. What is the time complexity of deleting the key floor of n divided by 2? Explain why. The tree height h equals n. Searching for floor of n divided by 2 requires traversing floor of n divided by 2 nodes, which is theta of n. The node has at most one child on the right side, so deletion after search is O of 1. Overall complexity is theta of n. This demonstrates the worst case for an unbalanced binary search tree. Question 1, tree after deletion as shown above. Question 2, pointer update rules, p left equals c or p right equals c. Question 3, theta of n time. These problems test understanding of the 3 deletion cases, pointer manipulation, and complexity analysis.